Hello everyone, thanks for having me. Today I would like to present a geographical visualization combining point feature labeling and word cloud. So map labeling is a challenge in map creation process. The task is to assign labels for geographical features like points, lines, and areas. And nowadays maps are not only with labels with geographical location names. There are various text-based geo-visualization. For example, this popular geo-word clouds, where the labels are placed inside a geographical region. The text-based geo-visualizations normally deal with massive data. There could be many repetition of this categorical labels. Thus, it requires information aggregation. There will be two criteria in conflict. From the perspective of labeling, we want to get a precise representation. So a text label should only cover its corresponding points. But from other direction, we want to get an abstract spatial pattern of the underlying messy data. So in some cases, we have to omit the outliers and sacrifice the precision. So in this work, we propose a hybrid visualization combining the precise labeling and abstract word cloud style, and try to get a balanced trade-off between these two criteria. So we begin with this geometric abstract problem. So given a set of color points, so a color corresponding to a category, to a specific label, we want to get a minimum set of pairwise disjoint rectangles such that each rectangle in this solution set cover points of a single color. So in this work, we show this problem isn't hard, so there's no hope to find a polynomial approach which could provide an exact solution. So to handle this problem, we first consider taking a set of rectangles as valid candidates. So in this work, we restrict our attention to minimum bounding box of every subset in this point set. So consider all the feasible geometric rectangle where each of its edge would touch one point. So this size could reach to n to the power 4, where n is the size of the point set. And furthermore, we consider additional constraints. For example, aspect ratio. We want the computed rectangle. We want to use it as the bounding box of the label text. So its width height ratio should similar to the shape of its corresponding text. And furthermore, for example, we also consider the tolerance ratio for the mispresentation. So there, when we compute the candidate rectangles, we could set multiple parameters to specify the definition of a valid candidate rectangle. Thus, we could customize the computed layout. Now we have a set of rectangles. We want to get a subset of pairwise disjoint rectangles. So that records as the weighted independent set problem in geometric intersection graphs. So this problem is defined as follows. So given a set of rectangles, so to each rectangle, a weight normally is a positive value is assigned, and in the geometric intersection graph induced by these rectangles, the vertices represent the rectangles, and two vertices will be connected by an edge if and only if their corresponding rectangles overlap each other. And the goal is to find independent set with a maximum weight sum. So back to our problem, we have a set of valid candidate rectangles, and then we could build the geometric intersection graph induced by this candidate set. And for a valid rectangle R, let PR be the set of points covered by this rectangle R, then we assign its weight as a specific polynomial function of its coverage minus 1. So here we just give the sketch idea of this reduction. Please refer to our paper to check the details, like how we define this weight function. Such that, for example, for this rectangle, which covers 8 points, we would assign 7 as its weight. Such that for a valid solution S, which cover all the points, its weight sum would be the specific polynomial function of the point set size minus the solution size. So imagine for optimum solution, so for minimum solution, its weight sum would be the maximum. So in this way, we successfully reduce our problem to a well-studied combinatorial problem, weighted independent set problem. So we could now use arbitrary weighted independent set solvers to solve our problems. And in our framework, we implement 2 weighted independent set solvers. One is an exact solver based on a weighted stat formula, and then we solve this stat formula with a weighted maximum weighted stat solver. This is an open source solver, MaxHS. And to compare with that, we also implement a greedy heuristic. The greedy idea here is greedily add rectangles with highest weight. So we first sort the candidate rectangles by their width in discreting order, and then try to extend the current solution by adding the heaviest rectangles iteratively. Then we did experiment to test the performance of these 2 weighted independent set solvers. For that, we generated 2 synthetic data sets based on a uniform and a multi-Gaussian point distribution respectively. Here is the details of the data set generation and the system specification in our experiment settings. So in the first set of experiment, we compare the running time of these 2 approaches. Here we set a time limit of 30 minutes, and as input size, we use the number of candidate rectangles, because now we only focus on this weighted independent set solvers. So in this plot, so the exact solver could only solve small instances, and the large instances would remain unsolved after 30 minutes. Compared to that, the greedy approach is very scalable and it's very fast. Like for large instances, it's almost a 4 order of magnitude faster than the exact solver. Then we want to compare the quality of the greedy solution and the optimal solution. Here we compare the ratio between the optimal weight, so the maximum weight computed by the exact solver, and the greedy solution weight. So by this experiment, our greedy solution consistently reaches more than 75% of the optimal weight. So in most of cases, it reached even up to more than 85%. So in one word, in our experiment, the greedy approach could solve the problems, like provide reasonable solution in a very reasonable running time. Then we apply the greedy approach on real world data, that is United States crop data in the year 2007. And by observing the computed visualization, we get two interesting observations. So first, our visualization is really a good combination of word cloud and labeling. So it's a precise labeling, but it could also serve as a nice geographical word cloud for this data set. And furthermore, if we take a closer look in this labeling, it's kind of the combination of area labeling and point labeling. So in the middle of the map, it's more like area labeling, and at the boundary is a classic boundary labeling or point labeling. So if you check the eastern coast. So motivated by labeling with information aggregation, we proposed a new geographical visualization combining labeling and word cloud. We also started its theoretical geometric problem, and we model it into weighted independent set problem. We did experiment and did a case study with real world data. For further information and open source code, please check our website. As future work, we think it could be very interesting to extend our current problem into dynamic settings. So for example, deal with dynamic inputs like streaming data from social media. Thanks for your attention.